Hi everyone, welcome back to yet another video. So today in this session we will be going to learn about this particular question from Codeforces round 379 div 2, and it was the fifth problem of that contest, and this problem is rated 2100. This problem will utilize the concept of the diameter of a tree and the compression of a tree to a smaller tree. The name of the problem is Anton and tree, and it reads like this: that there is a person Anton who is growing a tree in his garden. In case you forgot, the tree is a connected acyclic undirected graph. So there are a total of n vertices in this tree, and each of them is painted black or either white. So Anton doesn't like multicolored trees. So he wants to change the tree such that all the vertices have the same color, either all black or either all white. So to change the colors, Anton can use only operations of one type. We denote this operation as paint of V, where V is some vertex of the tree. So this operation changes the color of all the vertices U such that all vertices on the shortest path from V to U have the same color, including V and U. For example, you are given this tree, right? So if we apply the operation on the third node here, which is present here, as you can see, what will happen is that whatever nodes are connected to this third node, either directly or indirectly, and have the same color as that of 3. So here, as you can see, that 1, 8 and 9 are connected directly to 3 and have the same color as that of 3, that is white. And also this second node is also connected to this first node. So indirectly, this second node is also connected to this third node directly via the shortest path, which is also of the same color, that is white. So if we apply the paint operation on the third node, then it will simply invert the color of all of these nodes that I just mentioned. So this second, 1, 3rd, 8th and 9th node will turn black. So as you can see in this picture, these all nodes are turned black now. So in this way, we applied one operation and got this tree. But is our work done? No. Because Anton wants to change every node to the same color. But as you can see here, that still the 6th node is of the white color. So we want this node also to change to black color. So if we apply the paint operation on this 6th node, then what will happen? So since this 6th node, which is of white color, is not connected directly or indirectly to any node which is also of white color, so on applying the operation on the 6th node, it will invert the color. The color of this node will be inverted to black simply. And if this happens, then the entire this tree will be converted to black nodes. And in this way, we can say that the work is done. That is, all the nodes are turned black in this way. So how many operations are required in that case? So a total of 2 operations were required. First we painted the third node and then we painted the 6th node. And after doing these 2 operations, entire nodes of this tree are turned black. So we have to print here too, as you can see. So this is the same test case as that of this picture. Let's read further. So Anton is interested in finding the minimum number of operations needed as it needs to perform in order to make the color of all the vertices equal. So in the input, we have to first take the number of vertices in the tree, which can go up till 2 into 10 to the power 5. And the second line contains n integers denoting the color of each of the node. So if color of I is 0, it means that the ith vertex is initially painted white. So the white vertices represent the integer 0 and the black vertices represent the integer 1. And then follow the n-1 lines describing each of them, 2 integers ui and vi. So this will help to form the tree. And it is also given that it is guaranteed that all pairs ui vi are distinct, that is, there are no multiple edges, right? So in the output, we just have to print one integer, that will denote the minimum number of operations Anton has to apply in order to make all the vertices of the tree either black or all the vertices of the tree as white. So we discussed this example just now. If you look carefully about the second test case here, then clearly you can see that a total of 4 nodes are present. But the important thing to notice is that the color of all the nodes are already equal, which is equal to 0 here, that is white. So all the nodes are already white. And since Anton wanted the tree to have the same color for all the nodes after applying the operations, so here all the nodes are already white, that is of the same color. So it means that he don't need to perform any operations, and that's why the total number of operation he needs to perform is 0. So that's why the output is 0 here. So I hope you got the concept. So I hope you got the meaning of this question, what it is trying to find. So now let us try to go to the blackboard and try to understand it even in more depth for the same given picture. So let us now go to the blackboard. So this was the example that was given. As we saw that we applied two operations on this tree. First we applied the operation on this third node, and then we applied the operation on this sixth node. And after doing these two operations, the whole tree turned out to be a black nodes, right? What is actually happening if you see? So suppose I have applied the operation of paint of 3. So if I do paint of 3, according to the problem statement, what should happen is this particular node, that is this 3, will turn out to be black first. That is, it will invert its color from white to black. So this will get black, right? And if this node gets black, then every node also connected to it directly of the same color, that is white, will also turn out black. That is, it will invert its color. So this 8 will also turn black, this 9 will also turn black, and then this 1 will also turn black. And since this 2 is also connected to this 1 which is of the same color, so this 2 will also invert its color. So this white will also turn black now, like this. So if I draw it properly here, then, and since in this tree now every node is black except this node, that is the sixth node, so then after applying this paint operation, we will apply another paint operation on this sixth node. That is, we will apply paint of 6. So on applying paint of 6, this sixth node will also invert its color, and every node connected to it directly of the same color. But since this sixth node is only connected to this fifth node which is of the opposite color, so it means that the region in which the color will invert will only consist of this region, right? Earlier on applying the paint 3 operation, the color changed for each one of these nodes. Why? Because they were of the same color, right? But now since this sixth node is only consisting of white color and no node is connected to it directly of the same color, so the color will invert only for this region. So after this, the tree will look something like, this now. So as you can see that after applying these two operations, the whole tree has turned out to be black now. That is, all the nodes are black now. And in this way we can say that the total number of operations required to do this is simple 2. So that's why the expected output is 2 for this example. So let us now try to go into the depth and understand how we will solve this problem. So now I have drawn the tree like this in order to make you understand more better. So instead of drawing the nodes as complete black and complete white, I have simply marked each of these nodes with the color mentioned in this green letters, as you can see, right? So W refers to the white node and B refers to the black node, simple. So whenever I am applying the paint operation on a particular node, so the color of that node and each of the node connected to it directly of the same color or indirectly, but it has to be of the same color. So this is the condition. So all of these nodes are inverting their color simply, right? So if I apply the paint operation on this first node, so since it is of the white color, so it will see in each of its neighbors that which neighbors are of the white color. So since it has 2 neighbors, so it will see that this 2 is also of the white color and this 3 is also of the white color, right? But this 2th node, that is the second node, is connected to 4 and 5 which are both black. So it means that our paint operation will not go in this region anymore, right? It will be simply a part of this region only. Since this third node is of the white color, so it will see in all of its neighbors that which nodes are of the white color. So since this is white, but this is black, so it means that the paint operation will not go in this region and it will simply stop till here. So in this way we can say that if we apply the paint operation on the first node, then the inverting of the colors will only be done for this region, that is this region. I hope you understood this, and the same thing is written in the question also. Let me give you a scenario of the same tree in 2 different formats and ask you a question. So here, as you can see that I have drawn 2 different scenarios. So this is the original example given in the question, and I have drawn another version of the same tree here. How I have drawn this, let's see. So since you saw that it is mentioned in the question that whatever node you will paint, including that node, every node connected to it directly of the same color or connected to it indirectly will invert its color also, right? That is, for this given region that I have drawn here with red light color, so in this region if you change the color of any node, then it will simply invert the color fit for each one of these nodes, right? So that's why what I have done simply is I have represented this particular region as a single node here, which is this first node. Similarly, I have represented this region as a single node here, this region as a single node here, this region consisting of two black nodes as a single node here, this white node as here, and this region, which is the last region, here. That is, I have simply converted this given original tree into this, right? So you can imagine it something like I have given this particular region as a component ID of 1. So this is representing this particular region. Similarly, I have given this second region as the component ID 2. So I have represented it here. Similarly, I have represented this region with a component ID 3. So I have represented it here. Similarly, I have represented this region with the ID 4, which is here, and then this region with the ID 5, which is here, and then this region with the ID 6, which is here. So something similar to what we used to do in strongly connected component, that is, we divide the given graph into regions and assign IDs to it. So I have done the same thing here. But doing this, how it is beneficial? So since earlier we know that on changing the color of any one of these nodes, it will simply invert the color of every node present in this region, right? And if I do the same thing here for the node associated with this region, which is this node in our case, so if I do the paint operation on this node, then what will happen? So according to the requirement mentioned in the question, the color of this node and every node connected to it either directly or indirectly of the same color should also change its color. But since, as you can see, that this node is only connected to these 4 nodes which are of the different color, that is, they all are black, and since they all are black, it means that they are not a part of this region. That is, this region is an isolated region, so it only includes these 5 nodes and will not include any other nodes, right? So that's why if I apply the paint operation on this first node, then it will simply invert the color of this first node only, that is this node, from white to black. So if I do this, then let me do this parallelly to both of these trees so that you can understand what is happening. So if I do this, then this white will simply first turn black. And if I do the same thing to this region, which is corresponding to this node only, so what will happen? So it will again invert the color for all of these nodes from white to black. So they will also be black now. Now as you can see that in this tree, every node is black except this 6th node, right? So if I apply the paint operation on this 6th node, then what will happen? So the color of this 6th node will turn from white to black, but since it is not connected to any other node which is also of the white color, so it means that our operation will only be performed in this region. And if you remember, then corresponding to this region, I have drawn this node here in the second tree. So that's why if I also apply the paint operation on this node only, what will happen? The color of this will turn from white to black, right? And since it is not connected to any other node which is also of the white color, so it means that our paint operation will only be performed in this region, that is the individual node. So what has happened after applying these two operations on both of these trees individually? If you see, so each of these nodes present in this tree is now black. Similarly, each of the nodes present in this tree also now turned black. So what are the total number of operations we needed to perform in this tree in order to turn every node to black? Total operations we needed to perform were 2. And similarly, as I told, that the total number of operations we did for this tree is also 2, because the first operation we did was for this node and the second operation we did was for this node, right? And in this way every node of this tree turned black, which is what we wanted. So if I write, then the total operations required here was 2 only. So that's why what I'm saying is, instead of dealing with this particular tree, we will not deal with this tree. Instead we will deal with the compressed version of this tree, right? And it will give us the same answer required. So this is the first conclusion here. So let us now move forward and understand, if we once obtained this particular tree, then how we will use this particular tree now in order to get our answer. So if you remember, then this was the compressed version of the tree that was given in the question, right? So one thing important to observe in this compressed tree is that every two adjacent nodes have a different color, because we have represented it in the form of regions, right? So it is obvious that every two adjacent nodes will have a different color here. So you can take any edge and you will see that every two nodes are of a different color. So that's why if you apply the paint operation on any node, then it will simply invert the color of that node only and will not invert the color of any another node connected to it. So that's why if I apply the paint operation on this first node here, so it will simply invert the color of this first node from white to black. And it is true for each one of these nodes, because the adjacent nodes are completely of the different colors. So that's why it will only invert the color of that particular node. So now what I'm saying is, if I paint the first node, then it will invert the color of this white to black and not any other node, right? But after doing this, what has happened actually? I can say that this region now is now consisting of every node of the same color, that is black, and this is another region having a different color, that is white. So that's why what now I'm saying is, since we have applied the paint one operation and turned this node from white to black, so this region is now a one region, right? This is a collective region, and that's why we can represent this region now as a single node. So if I do this here, then I can say that I can represent this region now as a single node now, because this is what we did with the original tree also, and our answer didn't change. So that's why I am representing this particular region now here as a single node, right? And let's give it a ID of, let's say, 1. And this particular node is now connected to another node here, which is our 6th node. So this is of the black color and this is of the white color. So this black color now, that is the first node, or this node with the ID 1 is representing this region, right? So if the color of this node is black, so it means that whatever nodes are present in this region are also black. So our paint one operation is done in this way. And if you do the paint 2 operation, then what will happen? On doing the paint of 2 operation, we will invert the color of this 6th node from white to black. So this will become black, and once this become black, we can say that every node of this tree is now black. That is, this is now a one region, that is, this is a single region now. On doing the same in this compressed tree, for the 6th node, it will invert the color from white to black for the 6th node, so this will also black. So I can say now that this is equivalent to this, right? Because in this region, together within the boundary of this region, every node is of the same color, which is black here. Similarly, within the boundary of this region, every node is of the same color, which is black here. And finally, what I can do is, since I have converted this bigger tree to this smaller tree, I can even represent this region, which is consisting of 2 nodes of the same color, into a single node, right? So if I do this, it will look something like this. Let's give it any ID, let's say 1. It will be of the black color. So in this way, our paint 2 operation will also be performed successfully. So after doing these 2 operations, as you can see, what has happened ultimately. So what has happened is that our given initial tree, which was this tree initially, so this was given in the question. First we reduced this tree into this tree and we saw that our answer didn't change, right? So whatever number of operations you needed to perform on this tree will remain same on this tree as well, right? and then we applied the paint operation on this tree. So every time we applied the paint operation on a particular node, after inverting its particular color, if it is able to merge with its neighbors, then we simply merged that, right? And we got this even a smaller version of that tree. And similarly, after applying the second paint operation on this tree, we got this final tree which consisted of a single node. And since it consists of a single node now, which is of any either black or white color, which is black color in this case, so it means that our original given tree is finally colored such that all the nodes are of the black color now. So now suppose there was some tree and this is the compressed version of that tree, right? So if I apply the paint operation on this particular node, then what will happen? So it will invert its color from white to black, right? And if I do this, then clearly this node now will obviously match the color of two of its adjacent nodes here, which is also of the black color now, right? So that's why I can represent this tree now something like, so these three are now individual regions, if you see, right? So that's why it will look something like this now, in which the middle region is of the black color, this is of the white color, and this is of the white color. And again now, if I apply the paint operation on this node, which is of the black color, so it will just invert the color of this black node only. That is, it will turn its color from black to white. So this will become white. And on doing this, this becomes a single region consisting of the same color, which we can represent with a single node, which is this. And it will of the white color. So in this way we are able to reduce this compressed tree, right? So this was our compressed tree into this single node, and the total number of steps required to do this was 2. So this is our first step and this is our second step, right? So first we applied the paint operation on this middle node, due to which it accommodated 2 more of its neighbor nodes, and together these 3 nodes acted as a single node in the next step. Similarly, when we change the color of this node from white to black, the adjacent white colors are now a part of this component together, and that's why this region now converted to a single node, right? So that was our second step. So that's why we can say that the total number of operations required to do this was 2. This is the first operation and this is the second operation. So what actually has happened? Let me ask you one thing. What was the diameter of this compressed tree? So this was our compressed tree, right? So what was its diameter? So initially the diameter was, if you calculate, so it was 1, 2, 3, 4. So the diameter was 4 initially, and after I applied the paint operation on this center node, we got this tree. And in this, if you see the diameter, then the diameter is 2, consisting of these 2 edges only, right? And after we applied the paint operation on this center node, we got this tree. And finally, if you see, what is the diameter for this tree? It's 0. So I can say that the final diameter is 0. So one thing to observe in this is, every time we are applying a paint operation, the diameter is getting reduced by a factor of 2. So it got reduced from 4 to 2 and then from 2 to 0. So one important conclusion from this you can draw is, whatever paint operation or wherever paint operation you will apply on the compressed tree, the maximum diameter that can decrease is 2, right? So it can either be less than or equal to 2. So in what case the diameter will decrease by 1? Here if you see, then the total number of nodes that I have considered here was odd. So let's consider a case when the compressed tree like this consists of even number of nodes. So let's consider this case in which there are 4 nodes present, right? That is even number of nodes. And initially the diameter is 3. Why? Because there are 3 edges present, right? So if we start applying the paint operation one by one, then on applying the paint operation first on the center node, so since there are 2 center nodes here, which is this and this in this case, so we can apply on any one of them. So suppose we apply the paint operation on this node, so it will turn it from black to white. So this will become white. and as soon as it becomes white, then this will act as a single node now, right? Which we can draw it here. So I'm drawing it here, as you can see. So this will remain black and this will be white now. So in this way, our first operation is done successfully. Now we will apply the second paint operation. Since again both of these nodes can be considered as a center node, so we can apply it on any of them. So let's apply it on this node. So on applying the paint operation, it will turn from white to black, and if this has been true, then this will now act as a single node now, which we can represent it here like this. So in this way we have applied the second paint operation also. So initially the diameter was 3 for the compressed tree. Next time the diameter got reduced to 1, and then the diameter got reduced to 0. So if you see the difference, here the diameter is getting reduced by a factor of 2, and here again the diameter is getting reduced by a factor of 2. When the total number of nodes present or the diameter initially of the compressed tree was even, which is 4 here. But since here the initial diameter was 3, which is odd, so here first it got reduced by a factor of 2, and at last when the diameter will come equal to 1, then to get equal to 0 from 1, it will obviously get reduced by a factor of 1. So that's why based on this observation we can derive a formula in order to calculate the total number of operations based on the diameter of the tree. Since here the diameter of the tree was 4, so that's why I can say that for the even case, the formula for the total number of operations will be the diameter of the compressed tree by 2, because here since the diameter was 4 and it was getting reduced by a factor of 2 every time until it gets 0, so that's why 4 by 2 is 2, which is the total number of operations required to convert this compressed tree to a single node. And this single node now is just representing the entire original tree, which is now converted to a same color, which is white here, right? But if the case is odd, that is the diameter of the compressed tree is odd, then I can say that the formula for total number of operations will just be what? So it will be diameter by 2 plus 1, right? So since here the diameter was 3, so 3 by 2, 1.5, that is 1. So 1 plus 1, 2. 2 number of operations. So first operation and second operation. So if I have to write a combined formula for this, then it will just be, we have to take the seal of diameter by 2, or you can also write it as diameter plus 1 by 2. So this formula is same as this. So this thing is same as this, diameter plus 1 by 2. So if I apply the same formula here, diameter plus 1 by 2, so 4 plus 1 by 2, that is 5 by 2, that is 2 only, which is our answer here. Similarly, if I applied this formula here, so 3 by 2 plus 1, that is 1 plus 1, that is 2, which is our answer here, that is 2. So that's why this formula now will help us in order to find the total number of operations required to convert the given original tree or the compressed version of the original tree, for which the answer is same as that of the original tree. So once we are able to find the diameter of the compressed tree, we can use this just simple formula of diameter plus 1 by 2 in order to calculate the total number of operations, because we saw that in the compressed tree, whatever paint operation you will perform, you can only perform on a single node, and after this has been performed, it will merge with the neighboring nodes because of the same color, because of the afterwards same color, and will merge it into a single node. And since these two nodes are now becoming a part of this node, so that's why these two edges are now getting removed. You can imagine it something like this. These two edges are getting removed, that is the diameter of this tree is getting reduced by a factor of 2. So that's why it got reduced by a factor of 2. And in this case, when only 2 nodes were remaining, the diameter of this remaining tree was now 1. And that's why when we inverted the color of any one of these nodes, so it merged with the neighboring nodes into a single node, and that's why the diameter of this tree got reduced by a factor of just 1. So that's why 1. So this was the whole logic of this problem. So the same thing can be done for the original given tree as well. So let's do it. so that you can believe it what I am saying is absolutely true and correct. So this was the compressed version of the original tree, and we know that the answer that we will obtain after performing the paint operations on this compressed tree will be the same as the answer that we will obtain for the original given tree. So that's why we will start from this compressed tree only, right? If you see, then what is the diameter for this tree? I can say that the diameter can be something like either this or this or this. So in either case the diameter is just 3, right? So the diameter is 3, which will consist of 3 edges. So this edge, and let's say this edge. So the diameter is 3. If I apply the paint operation on any of the center node, let's say we apply the paint operation on this node, then what will happen? So after applying the paint operation on this node, which is of the white color, it will merge with its neighboring nodes. That is, this white will now turn to black, and because of this thing now will act as a single region or maybe a single node. And if I draw it, then this will now look like this, that is consisting of just 2 nodes. And let's give it a ID, let's say 1. So this is now white and this is now black. And now if you see, then what is the diameter? So the new diameter of this compressed tree is just 1, because just one edge is present. And if I apply the second paint operation here, so we can apply it on any of the 2 nodes. So if I apply it, let's say on the 6th node, so what will happen? So the color of the 6th node will now change from white to black. So if I do this, then this white will now turn to black. And after doing this, what will happen is that this thing will now act as a single node, right? So single node, let's say it as 1. So the naming does not matter whether it is 1, 2 or 100. What matters is the diameter of the compressed tree and the diameter of the subsequent forms, right? So now since it has been reduced to a single node, so I can say that the diameter is now 0. So how many operations do we needed to perform? So we needed to perform a total of 2 operations. First operation in order to go from this compressed tree to this tree, and the second operation in order to go from this tree to this tree. And by what factor does the diameter change? If you see, so clearly the diameter changed initially from 3 to 1, so by a factor of 2, and then the diameter changed from 1 to 0, so by a factor of 1. So first it changed by a factor of 2, then it changed by a factor of 1. And if I apply that same formula here, that is diameter plus 1 by 2. So since initially the diameter is 3, so I will say 3 plus 1 by 2, that is 4 by 2, which is 2. So this is nothing but the total number of operations only. So this was our first operation and this was our second operation. So in this way, just by knowing the diameter of this compressed tree, we can determine what is the total number of operations required in order to convert this compressed tree into a single node, because that single node will represent that the color of every node of the original tree is now same. So that's why this was a question of diameter of a tree. So I hope you really understood what I told in this video till now. So this is the whole concept. Now I think we should move to the code editor and code this up. So let's now go to the code editor. So initially first we have to take the input of the total number of vertices, that is n, and then we have to take the input for the color of all the nodes. So let me declare this color array here. So in this way we will take the input for the color of every node, which is either 0 or 1. The next thing we have to do is to take the input for the tree, that is n-1 lines. We will be given 2 integers representing the edge. So here a comma b, and let's form the graph now. So since it is a bidirected, so g of a dot pushback b, and then g of b dot pushback a. Right, so let me declare the adjacency list globally here. And since the total number of nodes can go up till 2 into 1e5, so that's why I will give it a size of, I think I should declare this color array also globally, so that we don't have to pass it every time, right? So this. And now once this has been done, let's move forward. So what I told you that once we have took the input of the original graph, we have to compress this bigger tree to a smaller tree, right? And in order to do this, first we have to divide the original graph into different regions. That is, we have to assign the component IDs to different regions. So our first step will be to assign the component IDs to each regions having the same color. So it's just a simple logic, nothing fancy. So I will go from 1 to n. and I will check that if this node is not visited, that is I have not yet explored this region, then I will call the DFS function from this node. I have to pass the ID here. So after passing this ID, every time it returns, the ID will get increased by a factor of 2 so that the next region is assigned with a different ID, right? So let me declare the ID here starting from 1, right? And let me declare the visited array also here globally. So let's start writing this DFS function now. So it will be a void type, and initially it is the node, and the second thing is the ID, like this. So the first thing we need to do is to mark it visited. So visited of node will be turned to true, and then we have to assign an ID now. But we have to assign ID to what? So let me declare another array here. Let's say the component ID, right? And let's initialize each value with -1 initially. So every time we visit a node, we will say that the component ID for this particular node is this ID, right? And then we will see into its adjacent neighbors. We know that for a particular region, every node present in that region will be of the same color, right? So that's why we'll check if the color for this child is same as the color of the node from which I am coming. And also one more thing to check is that it should not be visited, right? So this child should not be visited. So if it is not visited and it is of the same color, then it means that it is of the same region, that is of the same individual component. So I will again call a DFS function from this child with the same ID, because it will possess the same ID next time it is assigned to it, right? So once this has been done, I think I have written the DFS function here. And now let us move forward and do the next task. So once the IDs has been assigned, what we have to do next is start compressing the bigger tree to small tree, that is the compressed tree. So in order to do this, we'll use a simple logic here. So I will just simply iterate through every node, and then I will check what adjacent neighbors it is connected to, and then I will try to find the component ID for the parent and the child. So component ID of parent, which is equal to component ID of this I, like this. Similarly, I will try to find the component ID of the child. So once we get the component ID for both of these, we know that in order to compress the bigger tree to smaller, we will direct the edges between two different components if and only if they are having different IDs. So if it is not equal, then it means that we can direct the edge between these two. So let's say we declare a new adjacency list here similar to this G, and let's name it as, let's say, compressed tree. So this is the new adjacency list for the compressed tree. So I will say here that this compressed tree of something dot push back something, and again the same thing because it is a bidirected graph, right? So now between what nodes we will direct the edge? So we will direct the edge between the IDs we have assigned, right? Because the IDs were assigned very sequentially, that is 1 2 3 4 like that. So that's why this new tree will be formed between those IDs only. So suppose you have directed an edge now between a node of this component to a node of this component. So once you do this, then there is absolutely no need to direct any another edge from any another node of this component to any another node of this component, right? So in order to make sure that what we will use a set here. So it will be pair of long, and let's name it as lines, because lines are nothing but edges here, because it will help you to visualize it properly. So I will say that once a edge is directed from the parent to the child here, that is from I to C, I will push it into this set. Sorry, this will not be the parent and the child, rather than I will just push the IDs because now I am dealing with the IDs as the nodes and not the original numbering, right? So that's why we have to give a check here. The count in this set, that is lines.count, for this particular pair, that is from this parent to this child, must be 0. That is, they are not connected already, right? And the same thing we have to make sure from the child to the parent as well. That is lines.count from the child till the parent. So next, our task, if you remember, was just to find the diameter for this compressed tree, right? So our next task is to find the, so let us run a second DFS here. Let's name it as dia DFS because we are doing it in order to find the diameter. So we will start from the first node. So if you remember, then we can start the first DFS call from any node. So let's say we are starting it from the first node and the parent we are passing is -1, right? So if I write this function here, so this is our node and this is our parent, right? We will just check into the neighbors for this compressed tree for this node, that if this child is not equal to the node from which I am coming, then it means that we can go. So I will call this again like this, and this node will become the parent. And before doing this, since we need to store the distances from the first node or the node that we have passed to the next node, so that's why I will say distance of this child will be equal to the distance that has been took to reach this parent node plus 1. So let me declare this distance array here, and initially every distance is marked with 0. So once this has been done, our first DFS call is done. And after doing this, in order to find the farthest node that we have reached from starting 1, I will say the first farthest node, let's say it's -1, and then I will just check the whole distance vector one by one. Then our new maxi will be this distance of I, and I will say that this first farthest node is my I now. So this will become equal to I. So let me declare this variables here fast. So this maxi will be equal to initially 0. And once this has been done, we have got our first farthest node, and you must be knowing that what we do after this. So we will again call the same dia DFS, and this time we will start from this first farthest node instead, right? And before doing that, we have to make sure that the distance array is completely reset. So, and once this has been done, I will again do the same thing here, right? Also, we should reset the value of this maxi from whatever it is now till 0, and this first farthest node will be not required anymore, I believe, because we only need a diameter which is stored in this maxi variable. So this maxi is nothing but our final diameter. So that's why our final diameter is this maxi only, right? And once we have obtained this, I told you that the only thing we needed to print was this final diameter plus 1 divided by 2, which is our right shift 1. Now I think I have written the complete code, but I think we are still left with one edge case. So I want to make you imagine a scenario where we are just given with a single node. So if we are just given with a single node, then already whatever color it has been with, either black or white, every node is of the same color already, right? So the total number of operations required for this case will be 0. Or another edge case can be when every node present in the tree is already of the same color, either or black or white, right? So for each one of these cases, the answer will be 0, right? So in order to make sure this, just give a check here when the color values were assigned. So what we will do is, we will simply add all the color values one by one, right? So if this was the case, when all the colors were black, this 1 plus 1 plus 1 become equal to 3, which will be equal to the total number of nodes, right? And if the color values were white, that is 0 plus 0 plus 0, then it will be equal to 0, which is 0 only, right? So that's why if the value of check, which is the summation of all the colors, becomes equal to either 0 or the value of check becomes equal to either the total number of nodes, then it will mean that whatever the total number of nodes already present in the input are already of the same color. So the total number of operations we have to print in that case is 0, right? So let me declare this check variable. So just give a check here if the check value is 0 or n. So if this is the case, then just print a 0 and return. So now I think I have written the code. Let's run it to see if the outputs are coming or not. I think there is a mistake. Let me see. So I think I have found the mistake here. So this will not be node, this will be parent, right? Because we have to compare the child with the parent. If it is not equal, then it means that wherever we are directing the edge or wherever we are going is not the parent from which we have come. So now if I run this, then as you can see that all the test cases are getting passed. So now if I try to submit it onto the platform, let's see. So as you can see that our solution is accepted right now. So this is the code that we just wrote right from the very scratch, and I told you each and everything in very detail what is the logic behind all this code. So thank you so much for watching this video till this point. If you think you understood something new and found it valuable, please consider liking the video and subscribing the channel. So see you guys in the next video. Thank you.